Magnetic field force on a current carrying wire. Instead of just examining what happens to a moving charge in a magnetic field, let's take a whole bunch of charges, a constant flow of charges, otherwise known as a current, in a wire and see what happens. We introduced the horseshoe magnet in the last chapter. Now, every charge that moves will feel a magnetic force. So, you would expect the wire in which the charges move would feel a force in the same direction. As the charges are getting pushed, they're going to be pushing the other charges and atoms in the wire. So we're looking probably in the same direction the force is going to be. But let's think about it. Look at this picture to the right. The wire is in red. Here's the current flowing down, flowing across, and then flowing up. And then up here it's hooked to a battery or something. What are the magnetic forces on the three segments of the wire? You have this vertical piece of the wire, another vertical piece, and a horizontal. You have a uniform magnetic field going from north to south. We'll find the force on the wire by once again using the right-hand rule. But this time, place your fingers in the direction of the conventional current before you put it in the direction of the velocity of the positive charge. But since the positive charge velocity is the same direction as the conventional current, it's the same thing here. Then curl them into the magnetic field, just like you did for the moving charge, and then your thumb will point in the direction of the force. So we have three segments to worry about. Let's talk about the vertical segments first. And you can see up here we put a battery, we put little pivots here for this wire here so it can pivot about it, so it can swing. In this case, the current is in the absolute same direction as the magnetic field. That means zero magnetic force. They're parallel. How about this guy? Current's going this way, anti-parallel to the magnetic field, so the force is zero. The only force you feel is on this part of the wire. So when you put your fingers in a direction of the magnetic field, okay, you got your fingers like this, and then you curl them in the direction of the magnetic field, which is down. Let's see, it's hard to draw this. What you will have is your thumb now is going to come out of the board. That's the thumb coming out of the board. And here's the force. So the force on this piece of the loop is out. So the horizontal segment feels a force directed away from the magnet. And we have the battery and the two dots as pivot points. What do you think is going to happen to this current loop now? Again, summarizing, there's an outward force on this piece, no force on these two pieces. If you apply a force down here and these wires are free to pivot, this rod here, or this current carrying wire, will swing out. It'll keep going up until it no longer feels a magnetic field, and then gravity will pull it back. It'll probably push a little further back inside this until the magnetic field force once again pushes it out. So we have the thing kind of rocking back and forth. So what we've done is we took an electric current, a magnet, and started something rotating. Now, this isn't the best design in the world, it's just kind of a proof of concept. But what have we just invented? This is the beginning of a motor. Clearly, there's much more that you would have to do from an engineering perspective to make a real motor. Having a loop just go up and down isn't very valuable. Either in class now or for homework, look up how this configuration would be changed to make a real motor. Just Google motor. And while you're at it, you probably know that the earbuds from your cell phone have a tiny magnet in them. Look up how do music speakers work and see how this model works for producing music. The force on the wire depends on the current, the length of the wire subject to the magnetic field, and the magnetic field. Also the orientation. Once again, the only part of the magnetic field that contributes to the force is the part that is perpendicular to the current. So I is current, L is length of the wire, and B is the magnetic field. This actually comes from the QVB equation, the force on a charge Because let's just look at a quick dimensional analysis here. Velocity is distance over time, and then we put the b here. Let's just rearrange these things. What's charge divided by time? Well, that would be I, right? Rate of charge over time. D we can call the length of the wire, and here's b. So that's a nice way to do it if you forget this equation. But here we go. This is a force on a current carrying wire.